We are still at chapter 7. Now we are going to move on to chapter 7.84, which is the isentropic process. Yeah. So, what is isentropic process? Isentropic process is when the entropy is the same for S2, case 2, and for case 1. So, in a TS diagram, it would be plotted as a straight line like this because it's constant. Yeah, S2 equals to S1, right? Straight line. Yeah. So, it also means that during an internally reversible process, adiabatic, uh, uh, what do you call during an internally reversible adiabatic process, the isentropic process will be constant, which means the entropy will remain constant. So there is no irreversibilities. Yeah, there's no irreversibilities. Yeah, and adiabatic means there's no heat transfer as well. Okay, so let's move on to answering a question similar to this, yeah, for further understanding. So let's look at this question. Isentropic expansion of a steam turbine. Steam in a turbine. Expansion of a steam in a turbine. Okay. Steam hence is adiabatic turbine. Yeah. Adiabatic turbine at 5 megapascal, 450 degrees, and leaves at pressure of 1.4. So the first plot will be, how do we know that it is up here? Of course, we have to refer to the steam table. So you go to the steam table. What is this? Water, steam. Yeah, steam. So here we have 5 megapascal is 5,000. 5,000. The temperature, corresponding temperature is 263. In this case, how much is it? 450. So definitely this is a what do you call superheated steam. So that is your first one. Okay, and then leaves at pressure 1.4. Leaves at pressure 1.4. Okay, keep that aside because we don't know where is the 2, right? But this is an isentropic process. So if we know that we plot with TS diagram, it's going to be a straight line, but the temperature has actually dropped because the S is the same. S1 equals to S2. Okay, so roughly we know that it's going to be here. Okay, next let's solve this question. For a turbine, for a steam turbine, yeah, remember from the previous chapter, E in equals to E out. The next line would be MH1 equals to work out. Yeah, turbine produces work, and in this case, it's adiabatic, so Q is actually 0. Yeah, of course they didn't mention about the velocity, so K is 0, P is 0. There's no elevation in height as well. So leaving you with MH1 equals to work out plus MH2. Yeah, rearranging the formulas, you get work out equals to M H1 minus H2. So with that, we need to find the H1 and H2, right? Okay, for the first case, 5 megapascal, 450, you know that you need to go to the superheated steam to find the value. Okay, go to the superheated table. Superheated table. 5 megapascal, 5 megapascal, 555. 555. Oh, it's further down here. Okay, there you go. Okay, 5 megapascal. Temperature is 450. You're very lucky because you have the exact values, yeah, here. So what we have here, our priority is actually the H, yeah, H and the S. So copy that two values, bring it to here. You have the H and you have the S. Okay, for the second case, why do we even pick the S? Because it's isentropic, right? Because this S can be used for the second situation. Okay, so now we have 1.4 and we have the S1 value. Now we need to check, yeah? Go back to the steam table. So let me just write this down. Our pressure is 1.4 megapascal and our entropy is 6.82. Let's check this out. What state is it in? Go back to the table, our pressure table. Where's the pressure? Okay, that would be again 1.4 is 1400. 1400 is down here. 1400. Okay, and what is the entropy? 1400. The entropy just now was 6.8. So it's definitely exceeding SG, right? So automatically it is in superheated vapor state. So go back to the superheated 1.4. Okay, so we are now in superheated 1.4, and this is your temperature column. Okay, let's go back to the question. So this means this second state is also superheated. Okay, from here you can, from the table you can find your H2, right? Okay, where is that? We have 0.14, and we don't know the value of them, but we know the S. So where is the S? So the S is actually in between here, correct? Between 6.9 and, sorry, it's between 6.74 to 6.9, which means it calls for an interpolation. Yeah, so let me just snipe this. So how do you find your interpolation? 6.7, 6.9. Oh, I think I better snipe the whole thing over here. Easier. Okay, take that, bring here. Okay, you want to find the value of H2, isn't it? Yeah, so you need to do a bit of interpolation here. Okay, because you see S2, S2 which is equivalent to S1 is 6.8. 6.8 is actually sitting in between these two values, right? Correct or not? So you need to find the H. Okay? You need to find the H. So the H will also be in between. So how do you interpolate? I have very small column here, so I'm just going to interpolate what we have. 2927.9. We don't know. That's the H2. And then we have 3040.9. And then this will be 6.7488. And this will be 6.9553. And what we want is 6.8. 6.8210. Okay. So how do you interpolate this minus this? This minus this, divided by, divided by the whole thing minus, the whole thing minus. So divided by this one minus this one. Okay, so with that you can actually find the H2 value. Okay, it's a bit of working here. Okay, so what is the work out? Work out will be H1 minus H2. But remember, the value that's given to you is kilojoule over kilogram. Let me see what the question actually asks. They just want work output per unit mass. So don't worry. Don't need to multiply with the mass. You can just leave it as it is. So that's the method to actually solve the question. Okay. So next I'm going to move on to the last part of this chapter, which is the property diagram involving entropy. This is a very unique diagram. It's actually property diagram. Yeah, in this case it is enthalpy versus entropy. Yeah, enthalpy versus entropy. So for an adiabatic steady flow devices, the vertical distance of delta H on the HS diagram is a measure of work. Very unique. This is work, and the horizontal diagram will be the irreversibilities. Yeah, so always we want to keep this as much as lower, right? But we can't make it 0. Yeah, okay. So this is known as the Muller diagram. Yeah, Muller diagram. Now another unique part of the TS diagram, the area under the curve, the area under the curve represents the heat transfer for an internally reversible process. Yeah, so these are the things that you need to know from these two diagrams. With this, we have actually entered chapter 7. This is the end of chapter 7. Yeah, please answer the questions that I've actually given you. Okay, right.